systems which process events can be sometimes overwhelming and hard to understand. So even to completely understand when a given complex event is generated can be non-trivial. If you have some language for specifying complex events based on base events in the stream, it's sometimes not completely obvious based on the semantics of this query language what really will be matched. So there is a need for a formal query language semantics and tools for verification. Okay, so what we are using in our work is a certain specific form of symbolic execution. So this is a typical symbolic execution for ordinary programs. So the idea behind symbolic execution is that we execute the programs, but instead of feeding it the values, we really push through all the branches, the predicates and the constraints on variables. And okay, so here is an example. For instance, let's say X is unconstrained. We come into a branch. So depending on which branch we take, we add the constraints, and sometimes we may observe that some branches of the program are unreachable or may potentially satisfy conditions which we don't want them to satisfy. So this is a way to one of the ways to debug and verify programs. Usually what you are using here is some constraint or SMT solver, which checks whether it is the condition is satisfiable at all. Okay, so that's an unreachable branch. Okay, so our work which we are presenting here is a PatternExplorer tool and a simple pattern language which is based on non-deterministic automata with variables and constraint logic programming. We implemented its executable semantics in SWI Prolog, which is perhaps not the best implementation of Prolog, but it has a very nice package for producing web applications, and besides it's free. It permits symbolic, our tool permits symbolic execution using narrowing combined with the constraint solving. Narrowing is another way of symbolically execute things, which is useful in the context of rule systems, rewriting systems, this kind of things. Our tool compiles patterns which are vaguely regular language-like into a non-deterministic automata with variables. This regular language-like is about syntax, not about expressibility, strictly speaking. Compiled patterns can, of course, be matched with streams of events, but the tool is not meant as an event processing tool, but rather as a verification tool. So using narrowing, the tool can generate symbolic event sequences satisfying patterns, and the generated sequences can then be matched with another pattern to check if there are any unintended matching complex events. And one of the more interesting contributions is efficient representation of skipped events, which reduces the search space. User-friendly web interfaces provided, hence the use of SWI prologue. The direct inspiration for the language and partially for the semantics. We use somewhat different semantics, but the idea is, well, we are using different semantics, but the language is decidedly inspired by this work. We have some work on the subject published. Okay. So what about narrowing? So in the context of rule systems like term rewriting, logic programming, and so on, one of the most natural forms of symbolic execution is narrowing. So when we narrow, we unify the current state of the system with the head of the rule. So that's like the normal execution, and it is indeed if the current state is ground. However, the current state can also contain unbounded variables, and then the unification, in addition to producing some results, actually narrows those variables to matching terms in the rule. So you can see that it's really a form of symbolic execution. Because the executable semantics of our pattern language is given by automata, so let's consider this in this narrowing in the context of automata with variables. So first, automata without variables. So here is a finite automaton, and let us represent the state of the execution of this automaton by the pair consisting of well, automaton state, sorry for two users of state, and the list of unconsumed items. And based on this picture, of course, there are obvious transition rules. So starting from the state S1, we can consume A, passing to S2, and we can from S2 we can pass to S3, where L is here the variable. So and S3 is the final state. What about narrowing? Well, we can start from an unspecified list L0 and say initial state S1, and we can then check if by, I mean, not only check by narrowing, but actually produce the matched stream. Can we reach the final state? And as you can see, okay, so here in the subscripts, I will provide the substitutions for the variables. So it's like the constraints which flow with accrue with the execution of this system. So we start from completely unspecified input stream. And of course, the only applicable rule here is this one. So we unify, and of course, then we have our L0 narrowed to a more concrete input string. Then the only other rule is this one. We again unify, and then we narrow L2. Yes, here it should be L2. Okay, anyway, here it should be L2, we narrow L1, right? So, and of course, then there is only this rule which narrows, narrows L3, so we know now that this accepts the string A, B. Okay, so that's simple and somewhat unimpressive. So our automatons are automatons with variables which use composite states to store data, and their transitions are conditional. Conditions can refer to attributes of events. So let us consider, in a way of example, monitoring system for refrigerated storage units. So we can have unit types like C and O with some arguments. In this case, CID tau and OID tau are emitted when doors to unit with identifier ID are respectively closed or opened at timestamp tau, and temp is emitted periodically by a given unit to report its actual and set temperatures at the given timestamp. So consider the following automaton with variables, which now can, so this rule means that it can consume any event of type C and store this event in the variable X. Then it can consume any event of type temp and store it in the variable Y, which gets added to the next state. But this transition is conditional, and the condition here is that first off, both events must apply to the same unit. The actual temperature has to be greater than set temperature, so the unit is overheating, and it's after, say, 50 seconds after the doors were closed. When doors were opened, it's, of course, the temperature can increase, but say after this time, if it's still not below the set temperature, there is something wrong with it. So what you can observe here is that we're not only using variables which can be just simply narrowed, but actually those variables have attributes, say integer attributes, with narrowing, you can also narrow arithmetics, but it's not very efficient. There are better ways using, say, constraint solvers. So one prefers to mix narrowing, where we say narrow on type of event, with constraint solving or SMT. Now, nice thing about contemporary implementations of Prolog, perhaps apart from some strange one like Tau Prolog, which works in the browser, is that most of them implement some kind of constraint solving. The coverage is different for different Prolog implementations, but all of them cover at least integer constraints. So, and it covers them in the way where unification is already unified with the constraint solving. So Prolog seems to be a very good tool for this kind of thing, to implement it directly. Okay, so let us consider the example from the. Let us continue the example from the previous slides. So how now the unification goes? So the point is, now we are accruing not only, well, constraints, the substitutions from narrowing, but also the constraints from constraint solving. So first transition, we consume some C event, and that's just narrowing. We just narrow our input stream to the input stream with the door closed event at the head. But as you can see, this event has unconstrained parameters, and when we apply the next rule, we of course then do two things. We narrow the next event in the least to 10th, but we also have a condition, and this condition provides constraints for the parameters of the narrowed event. So, well, here I have already the same identifier. However, the remaining attributes are constrained by integer constraints. Okay. So, but that's not the whole story, because there is one complication, namely skipped events. So what's the problem? This automaton recognizes a situation where storage unit does not lower its temperature quickly enough after doors are closed, but the problem is that we cannot expect that there will be no other events between the matched events. So if we permit events between C and temp event, we cannot just say, we just ignore them, because for example, we have to forbid occurrence of a door open event for the same storage unit. because otherwise, okay, the door was closed and then it was opened again. So then our complex event is not about something being wrong with the unit, but the unit being opened again. It makes no sense. This is actually the query in our pattern language, and this can be this requirement can be described as follows. So first we have the closed event, then we have the temp event which satisfies the following this condition C, or should be rather, how have I denoted it as sigma, so it should be sigma, okay. Anyway, but this no skip construct means that there will be, between those two, there can be any number of events, but the open event which applies to the same unit. So, okay. So this kind of pattern can be recognized by, of course, adding loops with the skip condition, which do not advance matching, but at least filter relevant and irrelevant events. But then we have the problem when we want to execute this automaton symbolically. For we do not really want to generate all possible substrings of skipped events, like in this example where only second and last events are actually matched, because from the point of view of verifying this pattern, they are really equivalent. We're just generating a lot of spurious solutions where for each skipped position there is a separate solution, but it's just the same. On the other hand, we do not want to get rid of those skipped events, since, as I said before, some skipped events may provide witness to inconsistency of a given pattern with its intended meaning. Actually, what we do in our tool, we use matching streams generated by symbolic execution for verification purposes by feeding them to another automaton called testing or verifying automaton, which recognizes undesirable situations. And continuing this example, we can try to match the pattern from the previous slide against the following pattern, which matches door open event between the previously matched door closed and temperature measurement events for the same storage units. And we expect this pattern to fail because of constraints attached to each door open event skipped by the first pattern. But then if we are not intelligent about it, we need to consider a large number of spurious instances which differ only in irrelevant ways, and this we can hypothesize would slow down this kind of verification exponentially. So One solution is to leave skipped events as variables with attached constraints, so that symbolic execution would generate narrowed lists of events. So that's like here, where we have fully narrowed events which we actually match, and just variables in place of skipped events with attached constraints. But this is still not completely satisfying, as we continue to produce solutions differing only by the number of skipped events. So our solution here is to represent the whole sequences of consecutive skipped events as single variables with attached constraints representing information about the events which cannot be skipped in this part of the stream. And furthermore, if such partially instantiated list of events is matched again with another pattern, then instead of simply narrowing it, the list gets rewritten into a new list. I will give the example. In particular, a variable representing a sequence of skipped events may be rewritten to a sequence of partially instantiated matched events and other variables. So the example here is that we have already generated a list of events of this form. So we have event A of X, then we have some skipped events represented by a single variable with some constraints attached, and then we have B event. And when we apply the testing pattern, then we actually rewrite it, we can rewrite it as follows. So we can, of course, match the events already narrowed at least to a type, which perhaps will add some constraints or prove that it's impossible. But we can also match with this skipped sequence, and this matching actually puts some matched event inside. So now, where we had just a single variable representing a skipped sequence, we have now skipped sequence, narrowed event, skipped sequence. And of course, there are perhaps some new constraints attached to everything. Observe that this cannot be really done with ordinary narrowing, given the usual representation of lists, at least, since narrowing always preserves the current structure of a term and can only replace variables. But this really changes the structure. So this technique dramatically reduces the number of generated instances, and in particular, one can prove that the symbolic execution of automata over states can be topologically sorted with respect to edges other than skipping edges, because skipping edges are always loops. Always generates a finite number of symbolic solutions, and this of course means that their testing with the method outlined here is practically always complete. Well, I say practically always because of course the constraint solver will fail to solve particular constraints, but the data to consider is finite. Okay, here are the pattern constructs. I believe I have still 10 minutes and I need to leave some for questions, right?
Yeah, sure.
Okay, so I will just a few minutes. So we have prepared 3 implementations. The current one, which uses everything I said before. The abstract one, which narrows a single skipped event to a constraint variable, and the very concrete one, which leaves the parameter, which can leave the parameters of event as variables, but always narrows to the event type, and the reason why we consider that is that our first attempt actually used this kind of narrowing. And okay, so just a very short introduction to our testing setup. So here was perhaps somewhat more convincing example, also very small, but at least permitting some more interesting queries. So this is set up with the public transport management systems, where we note when the driver enters or leaves. I mean, the bus enters and leaves the bus stop, events of abrupt acceleration and deceleration, sharp turns, and drivers coming in and out. And of course, we have some example event stream to consider. We paired 2 patterns parameterized in lambda, and as you can see, this lambda is a parameter which regulates how much, at least, I mean, how much events we aggregate, so that we test the sort of looping construct, the iteration construct, and we have accordingly some testing patterns. And here are the results, which clearly show the superiority of the new solution. Can observe that this max length doesn't even go to the. Here I just couldn't wait to until for the bigger now. So okay, that's the example of our some screenshot from our tool. So when you input the pattern, what you get is an example stream, and you can see exactly which part of the stream the given narrowed event was matched with. There are also skipped fragments, and below there are constraints. So here are integer constraints, and here are constraints for the skipping variable. So the idea here is that this is a variable which occurs in here instance, or maybe yes. So that's this variable. There is another variable for technical reasons, which has to be a different variable, which occurs in the condition, and this condition is that you can skip any events except for events of this type which satisfy this condition. So this ref was really used for this dot notation I used earlier because, well, it was too much work to force Prolog to use dot for our purposes because Prolog already uses dots, so it wasn't this. Okay, so you can, so the tool is available. Thank you.
So, do we have any questions to the speaker? Please. Perhaps I have one question. So your automata is deterministic, right?
Well, yes, it is. Yes, it is deterministic. Yes. Or no. No, not. I just recalled the implementation. No, I am using just like implementing iteration and the choice. I am using all those epsilons and this standard stuff with the regular automats.
I see. So does your problem can be converted to recurrent neural network approach?
Okay, that's a very good question, and this is actually something we are thinking now because, of course, matching, searching for patterns is not so different than recognizing speech, where you really recognizing patterns in a stream of words, right? So, I believe that this could be done, perhaps. Well, whether with recurrent neural networks or something more allowing deeper exploration. Yes, this is a good point. I wouldn't use a recurrent network here because recurrent networks are not very good at going through long lists. So something like long-term, short-term memory networks or transformers probably would be better because of it. But before one does experiments, one doesn't really know. I can just surmise. One way in which one might go on about it is something we are now very much interested in, are neurosymbolic computation, which actually unifies the conventional statistical neural networks with logic rules. So this would be probably the way I would go about this. So, one could, for example, imagine because there are some symbolic inductive neural networks, which, like in inductive logic programming, just with neural networks can actually generate rules. So, for instance, one interesting suggestion would be to try to generate queries from examples of strings. So this would be a nice task for inductive logic programming neural networks.
Yes. All right. So
Yes.
I have a couple of small questions. First of all, you mentioned that this is for real-time application and if you have a repository inside Codona in my laptop, but which could be the average runtime for a problem with the buses for getting the patterns?
Okay, so in this case, I haven't tested it because, as I said, our tool is not the endpoint tool which actually analyzes. It's rather exploration of what can be done with symbolic execution of such a pattern languages, where of course you need to be fast, but you don't need to be real time.
And
So
in regards to that, how is the conversion time in the sense of if you double the input thing, how the program reacts?
okay, this depends on the rules. So one nice thing about how we deal with skipped events is that actually one thing which plagued our early implementation was a very strong dependence, exponential dependence on the number of event types, because of course when narrowing skipped events you just go through all the combinations, and this was unfeasible aside from very short strings to check. But now from our measurements, it's completely independent from the number of types. So this was really very nice idea, which made this whole thing actually feasible.
Thank you very much.
yeah, so do we have more questions or comments? Like comparing to different distributions is, I mean, patterns, I mean, in real world is like comparing to different functions, match or mismatch. So do you have in mind any set of family of distance between two patterns that you can account for?
I haven't actually thought about this. Thank you for the suggestion. No, and actually not sure whether I have seen any this kind of distance or fuzzy matching between pattern, but this would be certainly something to look for. Thank you for that.
You have like two, you have a snow, the pattern of flake of snow. They are never the same two patterns,
yes.
but it still does make sense to make a kind of distance measure between them.
Yes, well, the point is this, it's not completely obvious how to do, because for, say, words, you have, of course, this standard word distance, but here observe that each element of the stream contains also data attributes. So this would require also using some metrics on the attributes. And the point is, another big thing which complicates this situation are the skipped events. So note that here actually most of the events in the stream doesn't matter. So we have two completely distinct streams, but which may have a similar, actually matched parts. So it's not easy to think about such metrics.